Okay. Okay. So remember what we're talking about. We're talking about series. We're talking briefly about power series and radii of convergence and that sort of thing. Now we're going to flip back and just talk about series in general. In particular, we're going to talk about these sort of like, maybe we should call them product series. Just, maybe it's best, what we're really talking about is, so we'll be talking about things that I maybe can call product series. In particular, the first thing we'll talk about are series of the form summation A sub n, B sub n. Okay, series of products of sequences. Okay, so, okay, so what's going to be useful for us? This is not going to be exciting, but this, the following lemma, which is pretty straightforward, is going to be useful. And maybe the way to talk about it is to say that, let's call it like a characterization of the tail. The partial tail. Okay, so here's the theorem. You have two sequences, A sub n and B sub n, and you let capital A sub n be the partial sum of the a's. Okay, so k from 1 to n. Okay, and for convenience, we're going to denote A sub negative 1 as 0. Okay. And then the claim is the following, that if you take the sum of the A sub n, B sub n's from n equals p to q, right? So this is like some finite section of the tail, right? Right, some finite section of the tail. Then there's a convenient way to express it, okay? And that is, you can express that in terms of the partial, partial sum of the a's as follows. It's a summation from n equals p to q minus 1 of an times bn minus bn plus 1 plus a sub q b sub q minus a sub p minus 1 b sub p. Okay, so this is basically, here we've got these, finite section of tail. And then we express it in terms of mainly the partial sum sequence, partial sum series, the partial sums of, partial sums of the A sub k. Okay. Why are we doing this? This is basically a tool, and we'll use this a couple of times in what follows. Okay. Yeah. So it's just a technical tool, just a lemma. We'll create it, we'll use it, and then we'll forget about it. Okay. Okay. So the proof is actually pretty straightforward. So you say, well, let's look at this thing. A sub n, B sub n from n equals p to q. So the first thing we do is we say, well, we're going to express A sub n as A sub capital A sub n minus A sub n minus 1. Right? Right? Because this is the sum up through n. We subtract off the sum up through n minus 1. That just leaves the top term, A sub n. Okay. That's the first thing we do. Okay. And then we multiply it. We distribute. A sub n, B sub n equals p to q minus summation a sub n minus 1 b sub n equals p to q. Okay, so nothing really happens. The next thing we do is we shift the index. So we say, let's make the index, let's rewrite this guy as n goes from p minus 1 to q minus 1. Okay. And that makes, that shifts the index up by 1. So we get a sub n, b sub n plus 1. Okay, so we just re-indexed it. Nothing else. N equals p, q. This one we keep, minus that. Okay. So then we separate it, right? So then what we do is we peel off the top term here. We say, okay, we're going to write this as n goes from p to q minus 1, a sub n, b sub n, and we pull off the top term. The top term is aq, bq, right? And what we do here is we add on a bottom term. So we say, let's go from n equals p to q minus 1. Right, this goes from p minus 1, so we're peeling off that bottom term. What am I doing? So it should be subtract, yeah. P minus 1 p n p. Thanks. Yeah, because these things combine together to give you this thing. Sorry. Temporarily insane. Okay, and then you see what happens, right? You just put these two guys together, right? You combine those two guys together, and you get this. You distribute out. So that's it. Okay, so yeah, so there's this lemma. Okay, and as you see, there's really nothing to this lemma, right? It's just re-indexing and then separating out some terms. Okay, but it's handy because it expresses this thing, which is in terms of little a and b, in terms of big A and little b, right? So we can, if we know stuff about the convergence of the A's, then we can invoke that. Okay. This allows us to use the convergence of the A's. Okay, I'm going to erase this. Okay, so okay, so now here's what we're going to use it on. We're going to use it to create a tool, another kind of tool. So so here it is. If you know that the a sub n, which we'll define in the same way as before, if the a sub n are bounded, if 2, the b's are decreasing, and 3, the b's limit is 0, then this product series converges. Okay. Okay. So let's think about that. Okay. So what we're going to use is, we want to show that this thing converges. What we're going to use on it is the Cauchy criterion. Okay. So we say, okay, we want to show that for all epsilon greater than 0. There exists an n such that if p and q are bigger than n, then the size of the tail from p to q is small. Right. Right, that's the Cauchy criterion, right? That's exactly the Cauchy criterion. So, and you see why we created this thing. Okay. So, okay. So we say, well, look, consider, this thing that we're trying to control, we can of course rewrite using the lemma, right? This is the lemma. I'm going to say that I'm going to use the lemma, and I'm also going to use the triangle inequality. Or maybe I'll just use the lemma first. Sorry, I use the lemma, which says that I'm going to do both at the same time. Sorry. So right. So use the lemma and the triangle inequality, and say, well, this thing is smaller than the sum of these guys. Right? Okay. Okay, so far so good? Yeah.
Wait, why is the summation only in front of that first term?
Summation is only in front of this first term.
Oh, okay.
Right. This goes from here to here.
Got it.
Yeah. Remember, these were the terms that we just peeled off of the sums.
Right. Okay.
Right. We just pulled them out of the sums. So it was this guy plus this, and this guy minus that. Right. So yeah. Okay. So we're trying to make this thing We're trying to make this thing smaller than epsilon, right? Right. We want to find an n past which this whole thing is smaller than epsilon, right? So what are we going to use? Well, we can use that the partial sums are bounded, right? So we know that the a sub n's are all smaller than some m, right? So we can rewrite this as this is smaller than summation as m times summation bn. This goes from p to q minus 1. This is bn minus bn plus 1 in absolute value plus m bq plus m bp. Right? Let me just pull the m out here. Right? Okay. But the b's are decreasing real numbers, whose limit is 0, right? So these are all, I can get rid of these are all positive numbers, right? These guys are positive numbers. I don't have to put absolute values on them. Right? They're positive numbers. And also bn minus b plus bn plus 1, that's also positive because these are decreasing, right? So I can get it in absolute values there. Okay. Okay. So, right, and this goes from n equals p to q minus 1. Okay. So, anybody see what happens? Something nice happens. What happens to this sum here? Right? We get bp minus bp plus 1. Right? We get bp minus bp plus 1 plus bp plus 1 minus bp plus 2, et cetera, up to the top term, which is going to be bq minus 1 minus bq. Right? You guys see what happens? Collapses, right? You have a telescoping sequence, right? And what you're left with is just a bp and a minus bq at the end. Right? right? For this thing here. So this is a telescoping series, right? Collapses. Okay. And then we have a BQ and a plus BP at the end. Right? The BQs cancels that off, and we get 2 BP. Okay. So we get less than or equal to 2 BP. Okay. Now remember what we're trying to do. We're trying to find a time past which this thing is smaller than epsilon. Well, why can we do that? Why is that clear? What do we know about the beasts? And
They converge to 0.
they converge to 0.
Yeah, so
yeah.
value.
Yeah. So, right, we know that those guys go to 0. So choose n such that n bigger than n implies that that the size of Bn is smaller than epsilon over 2n. Right. Once you choose that n, then this thing is going to be smaller than epsilon. Is that okay? Okay. So that gives us so this technical lemma gives us this kind of tool to use on these sort of product series. Okay. Okay. So okay. Any questions about that? Right. The main thing was that we had that lemma, right? The lemma, then we used the triangle inequality. We used the triangle inequality, and then we just used the terms of the hypotheses, right? So we said, oh look, the partial sum sequences are bounded, so we can pull that thing out, and then these guys were decreasing numbers, and so we can get rid of the absolute values, things telescope, and that's the end. Okay, so there's this theorem, and we'll use this theorem to get two results. So applications. So the first application is what you may have seen years ago as Leibniz's theorem. So-called alternating series theorem. So if you have a series, and if one, let me say it this way, the odd terms of the series are all positive or all non-negative, and the even terms of the series are all non-positive. Right? So it's an alternating series, is what I'm saying. Right? If you have an alternating series and the size of the terms decreases to 0, then the series converges. Okay. And the proof of this is more like a corollary of the theorem. It's an immediate consequence of the theorem, right? What you do is you say, well, look, what we're looking at is proof. think of the series as summation -1 to the n, -1 to the n, absolute value of c sub n. Right. C sub n is, each c sub n just equals this, right? It's going to be its absolute value, right? It's the absolute, these are real numbers. Right? Otherwise, it doesn't make sense to say greater than or equal to 0. Right. So when n is odd, you have a negative number times the size. You get c sub n. When n is even, you have a positive. You have 1 times the size, which is just c sub n again. Okay. So right, and then you're done. Right. This is your a sub n, and this is your b sub n in the previous theorem. Right. The a sub n are bounded because you're just summing -1 to the n, right? So it just bounces back and forth, right? So summation -1 to the n, these guys are definitely bounded, right? Because you're just summing -1s and 1s in alternation, right? And then these guys satisfy the conditions, right? They're decreasing positive numbers whose limit is 0. So you're done. Okay. So Leibniz's theorem. Okay. Another application. Another application. For power series, this thing, a power series with radius of convergence 1. If if the coefficients are decreasing real numbers whose limit is 0, then the power series converges on the boundary. Except at 1. Okay, so you have a power series, right? So what this is talking about is you have a power series, and you know that it has a radius of convergence of 1. So it converges inside the unit disk, right? And this is saying that under certain conditions on the coefficients, you can tell that it'll actually converge on the boundary as well, except at here, except at 1. Okay. So for example, if we consider summation z to the n over n, right? Right, if we consider this thing, right? Remember how you get the radius of convergence, right? You look at the lim sup of the nth root of the nth coefficient, and you take 1 over that, right? That's the radius of convergence, right? Well, this thing is going to turn into 1, this thing turns into 1, and so the radius of convergence of this is 1. Okay. So you know that the radius of convergence of this thing is 1, but from this theorem, you also know that it converges on the boundary, excepting at 1 itself. And in this case, you see that it fails to converge at 1, right? Because at 1, you're going to get the harmonic series, which doesn't converge. Okay. Okay. So, the proof is in the previous theorem, let a sub n be z to the n and b sub n be c sub n. Okay, so the c sub n clearly satisfy what we want them to, right? They're decreasing and they decrease to 0. What we do need to show is that the partial sums are bounded, right? Are the partial sums of the a sub n bounded? Well, right. So it suffices to show that that these guys are bounded. Okay. Well, are they? Well, the partial sum is going to be z to the k from k equals 0 to 0 to n. Right? We've seen that before, right? This is just a geometric series. Right? This is just a geometric series, and so what you get is 1 minus z to the n minus 1, n plus 1 over 1 minus z. Okay. So is it bounded? Well, the top is smaller than 2, and the bottom is just the absolute value of 1 minus z. Right? Because z. We're looking at z with magnitude 1, right? So when we take the absolute value of this, right? Right. This is, you just use the triangle inequality. You get 1 plus the absolute value of z to the n plus 1 over 1 minus z, right? And this is 1, so you get 2 over absolute value of 1 minus z. Okay. And so, yeah, the partial sums are bounded. They're bounded by this thing. Okay. So, yeah.
Why did this only work on the unit circle and not on like a radius convergence like 5 or something? Because wouldn't the same logic apply?
Yeah, no, it will work. Yeah. So if you have a power series, yeah, no, it'll still go through.
Okay.
Yeah.
So any circle.
Yeah. So I guess let me make sure I'm not lying here. No, it won't work. It won't work because of this n plus 1. Right? Right? Because you would be doing this on some z equals 5, say.
Mm-hmm.
Right? On the radius 5 circle, you're going to get 1 plus 5 to the n plus 1. Right?
Mm-hmm.
And that's not, as n increases, you don't have an upper bound. Right? Fortunately for z equals 1, no matter what power, this is still going to be 1. Okay, let me, is this making sense? Kind of, right? We're trying to show that this thing converges for every point on the unit circle, right? So we choose a point on the unit circle not equal to 1. And we say, well, let's look at it, right? We have to show that these guys are bounded, right? But we have an expression for this that's just this. We can bound it with the triangle inequality, and then since we're on the unit circle, this thing becomes just a 1, and we can bound it with a 2. So for every point z, there's this this sequence converges. The series converges. Yes, Anne?
Does this theorem mean that we don't know anything about when z equals 1, or that it does not converge when z equals 1?
This theorem tells you nothing about when z equals 1, but it could happen the other way. So for example, like if you look at, say, z to the n over z squared, I'm sorry, over n squared, right? Again, when you take the radius of convergence, you're going to get the nth root of n squared. Well, that's still going to be 1. Okay, so this is one of the this is a power series with radius of convergence 1. The coefficients are decreasing to 0, right? So we can apply the theorem, and we know that this thing converges on the disk, excepting at 1, right? But this guy actually does converge at 1, right? Because if we put 1 in here, we get summation 1 over n squared, which is actually finite, right? So this guy actually converges on the entire disk, including the boundary, whereas this one converges the entire disk, the closed disks excluding 1. Yeah, so it could happen either way. Okay. So okay, I was hoping to get through to something to the other kind of product series, so-called Cauchy products. But I guess we'll do that next time. So next time we'll deal with another kind of series product called this is a more genuine, a true product of series called Cauchy product. That will be the end. That will basically be the end of this chapter, and then we'll go into chapter 7. How much more time do we have in the course? How many more weeks do we have?
3.
2.5, right? Right?
Yeah.
So 2 and 2 days, right? Is that right? Okay. I'm not sure if we'll get through everything, but there's no reason to try to get through everything, right? At the cost of understanding. So we'll go through, I think, a fair part of chapter 7. We may not get to the crazy theorem of Ascoli-Arzela, but that'll be okay. Yeah. Okay. See you guys next time.